Hello, this is a video I wasn't really considering making, but I've had quite a lot of requests to look at how can we implement texturing into the graphics engine that we've been developing over the previous videos. I've always been a bit concerned about texturing because it requires high spatial resolution and high colour resolution, both things the console lacks. And so even though we can talk about the theory of how texturing works, I was a little concerned that the end result might be underwhelming. However, after some experimentation, I think I've come up with a result which is quite interesting, and so it is a bit video worthy. I've also oddly mentioned in the past when people have asked me to talk about depth buffering that I'll only do that when I talk about texturing, which, with having no intention of talking about texturing, probably meant I wasn't intending to talk about depth buffering. Think of the logic of that later. But I have decided to add a depth buffer too, because it's very simple once you have a texturing system in place. Fortunately, texturing is quite simple. So let's just get stuck in. And as usual, I'm just going to start exactly where we left off from the previous video in the series. We had a landscape we could move around with a first-person 3D camera. But we can see that the landscape is a bit void of texture. And just in case you're not familiar with what texturing is at all, texturing is the effect of painting an image into the polygons. So we can see here that all of my polygons, they're flat shaded, a single colour. But in lots of games today, you prefer to texture them to make them look more realistic or to give a particular effect. And just for proof, this is exactly where we're starting off, part 3's source code. So let's start by just considering what texture is. Well, texture is just an image. It's an image like any other computer image you've used, with starting 0, 0 in the top left and 1, 1 in the bottom right. We could consider a texture to be an OLC sprite in the console game engine, something we've used plenty of times in previous videos. And so here I have a texture of a wall, but let's say in my game I want the wall to appear, then the easiest way for me to do that, because we've been thinking about triangles, is to render a couple of triangles and somehow paint onto those triangles the texture of the wall. And so, as well as our triangles having vertices in 3D space, which is local to the model of the wall, we have an additional set of vertices which exist in texture space. And these new vertices map directly to locations within the texture plane. And so when we render the two triangles, we can infer that one of the triangles will have the top left half of the texture, and the other triangle will have the bottom right half of the texture. And so therefore, by specifying a particular image to be the texture, and looking at the additional coordinates that we'll add per vertex of our model, we can decide which regions of an image to paint onto the polygons. One of the cool and useful things about texturing is our triangle doesn't have to occupy the full texture. In fact, it can occupy any sort of space within the texture itself. So in this case, when we render the quad, we're extracting a small portion of the texture. I'll clumsily try to replicate what that might look like when we draw it. We have a big long line down there, and we have another line down there, and this top corner's coming in there. I've got a line going across there, something like that. And this means we can manipulate texture coordinates to provide interesting effects. And it also means we can have one texture with lots of different types of images in. So we only need to load one texture into the system, but we can make an object look like lots of different things. And this is much simpler than specifying textures individually. So let's say you have a complicated character in a platform game. Rather than specifying a texture for the eyeballs, a texture for the clothes, a texture for the shoes, a texture for the face, you just have one single texture which represents the entire model. And we choose locations out of that texture as necessary, using texture coordinates per vertex. In relatively modern computer games, it's not uncommon to have many textures per model in lots of different detail. Modern graphics cards really rely on textures to give that unique look and feel of realism on the subjects that are being rendered. So it's not just really an image layered once. There could be multiple images layered on top of each other, and values of the pixels within those images used to go on to do secondary computations. So things like lighting calculations and the fuzziness of how an object should look and how should it reflect a particular type of light if the material is wet. So all of these far more complicated calculations are all based in the texture domain too. For this video though, we are just going to simply paint a texture onto a polygon, but we'll use this as the basis for more interesting effects later on. We ended the previous video by loading an object file into a mesh, but we'd also removed the cube code. I'm going to put back the cube code because I think we want a simple object to think about whilst we're manipulating textures, so I'm just going to cut and paste that back in. But we have to make some changes to it because we added a fourth value to our vector 3D type. And given that the cube was constructed out of initializer lists, we need to include a fourth value initializer into the construction of the mesh object. And this is quite tedious, so I'll try and speed it up. Let's just make sure that still works with our first-person camera framework. And yes, it does. We can see the cube has been shaded on different size, different intensities. Okay, fair enough. Along with our vertex information, we want to store the texture coordinate information. So where in the texture does that particular vertex lie? And of course we only need a 2D variable to do this because textures are a 2D thing. We already have a struct vec3d. I'm going to add an additional struct vect2d, but rather than x and y, I'm going to use the notation u and v because this is common parlance in texturing. I think it's a little throwback to texturing being done in normalized space. So typically the entire width of a texture is 1 and the entire height of a texture is 1. This now means that our triangle object has some additional information to store. So I'm going to create a new variable of our new type vec2d called t to stand for texture coordinates, and of course we'll have a set of 3 of them per triangle. Naturally, this means we need to add more data to our initialization lists now, as we need to accommodate the new texture information. Fortunately, this is quite simple, as here I have the 6 faces of a cube, and I want each face of the cube to represent the entire texture. That means I can duplicate the coordinates. Now that I have this additional texturing information in my triangles, I need to make sure that whenever I'm moving triangles around in the rest of the code, I'm also copying over the texturing information. For example here, when I am transforming my original object vector by the world matrix, that's fine, I get the transformed vectors out the other side, but I also need to then copy over the texture coordinate information, which is untransformed by the matrix. The same applies when we go from world space to view space. And naturally, we also want to do it when we're going from view space into projected screen space. But there's a problem here because we have a clipping routine that gets in the way. We have to adjust our texture coordinates for any lines or edges of triangles that have in fact been clipped. Simply put, consider a triangle as normal in our system, and we pass through a clipping plane to chop the triangle into several pieces. We create new vertices for our new triangles. And don't forget, in this instance, we generate 2 new triangles on this side and 1 new triangle on that side. But we also need to calculate our new texture coordinates for these new vertices. Unfortunately, this is quite simple. So assume that this is u1 and v1 texture coordinate, and this is u2 and v2. A byproduct of the clipping algorithm is that we look at whether the lines intersect with the plane. And some of the data that we get out of that actually reflects this, which we call t, which is a normalized value between 0 and 1 along the line between the 2 points, which in this case looks to be about 0.5. Therefore, we can easily calculate this intercept point in texture coordinate space as being, we'll say v prime equals v1 plus t, v2 take v1. And naturally the same applies for the u coordinate too. So I'll now modify our clipping algorithm to give me back this t value so I can perform these calculations to create new texture coordinates for our clipped triangles. Inside our vector intersect plane function, we can see where we calculate t, the normalized distance along the line between the 2 points where the intersection has happened. So I want to expose this value to the outside world, and I'm going to do that by passing in a reference to a t variable here. So t can be posted back to the caller of this function via one of the arguments. And the only times I do call it exists in our clip against plane function. There's quite a lot to do in this function, because if you remember, we created lists of how many points were inside and how many points were outside of the clipping plane, in order to know how to then generate further triangles. We just need to make sure that the additional information also flows around. So as well as just having inside and outside points for vertices, I'm going to have inside and outside points for texture coordinates. Now, the vertices are what lead this. The texture coordinates are always slaves to the vertex coordinates. And because the texture coordinates are always slaves to what's happening to the vertices, I can just simply add in additional code here which mirrors how we handled the vertices in the first place, classifying the texture coordinates as either inside or outside. The next stage of modification is to actually calculate the new u and v coordinates when we need to. So we know if that all the points lie within inside the plane, we don't need to clip anything, nothing changes. And if all the points lie on the outside of the plane, blah blah blah, same thing. But when we do need to clip things, we also need to generate new texture coordinates at that clipping point. And I'm going to need the variable t that we calculated to do this. So I'm just going to pass in t into these two functions, which are calculating the intersection point of the plane and the line, which is one edge of the triangle. But I haven't written any code yet to handle my new vector class, which is only 2 points. We did it for 3D vectors. So I'm going to have to go back to the old way of doing things and calculating things line by line and manually. Firstly, we'll consider point 0 of the triangle. Nothing changes here, so we just want to make sure that we keep the texture coordinate corresponding to the point. We're going to add in some lines now that calculate the calculation we've just seen in the slides. So we've got t times the distance between the 2 points in question, offset by the starting point, to give us a point in texture space of our new vertex coordinate. And in this case we need to generate 2 new texture coordinates, so it's very similar. We just need to change the indices. I'll make the same modifications to the other side of our function where we're outputting a quad. This means we can get back to what we were doing, which is handling the textures from a view space to a projected space. And now the clipped triangle texture coordinates get accommodated too. Finally, we get to the point where we're drawing the triangles onto the screen. And up to now, we've used 2 functions provided by the console game engine called fill triangle and draw triangle. And neither of these are any good to us anymore. I'm going to keep them here because they're useful for debugging. And I'll set the draw triangle outline to be white. So we're really going back to the start here. Let's just make sure everything's still working. And there it is. The original cube. We need to create a brand new function to handle the drawing of textured triangles, because this is something that we'll have to handle on a pixel by pixel basis. There are a handful of methods for rasterizing triangles to a screen. And by rasterizing I mean the process of filling in the pixels that represent the inside and boundary of the triangle. And it's important that we choose a routine that allows us to get pixel by pixel access, because for every single pixel in the triangle we're going to need to sample our texture in a specific location. And by sampling the texture, I mean get the colour of that particular pixel, or in the case of the console, get the colour and the symbol of that particular pixel. The algorithm for drawing a triangle in this manner is pretty straightforward, but if we start backwards, what we can see is we need a list of points that represent the starts and ends of horizontal lines. Because once we have the starts and ends of horizontal lines, we can then iterate per pixel along a single row on the screen and draw it properly. And so step 1 is that given 3 arbitrary coordinates that represent the triangle, is to sort them vertically, so that the lowest y value is at the top of the screen. So there's x1, y1, x2, y2, and x3, y3, where y1 is less than or equal to y2, which is less than or equal to y3. And this is an important first step because it tells us how many rows our triangle occupies in its 2 distinct parts. If we take the vertex that's in the middle, and we know which one that is because we've sorted it, and draw a horizontal line across the screen, we know that this is also the point that we might need to change some of our calculations. So y2 take y1 is quite a useful thing. Naturally, the same applies to y3 take y2. We know when to start and stop our algorithm in the y domain. If it happens that our triangle is indeed flat to begin with, so let's say the triangle looked like this, we've only got 1/2 of this whole shape to draw, and we can determine this flatness by looking at the difference between y1 and y2. If the difference is 0, we've only got half a triangle to draw. But let's leave that for a minute. We now need to calculate the starting points of our horizontal scan lines. And given the information that we have here, that's quite easy to do. We can assume we've got 2 lines that make up our triangle, A and B. It's quite easy to work out the gradients of A and B. It's just a simple calculation, such as x2 take x1 by y2 take y1, dy by dx. So this means that for every step down we take, which we know is going to be an entire 1 row at a time, there's a certain amount of x that we need to move backwards. And so as we scroll through our scan lines from top to bottom, we can work out where our starting point is. And in a very similar way, we can work out where our ending point is for B. And filling in a single row of pixels is of course entirely trivial. We just loop through the starting point to the end point and set them. When we get to our y2 coordinate, we can see that our lines have changed. A is no longer necessary, so we'll reuse the data structures we've got and rethink about how A is calculated. Fortunately, we've already done all of this for B. We don't need to do it again. Nothing has changed here. The gradient for B just carries on doing what it was doing before. But our shift along the x-axis for A has indeed now changed because the gradient of the line has changed. So it's important we calculate that, and as before, we just scan across with a simple for loop, knowing the start and end points of our triangle. And indeed, if you look at the OLC console game engine source code, you'll see this is precisely how the fill triangle works. But it makes an assumption that the contents of the triangle are homogeneous, they're all the same. And sadly, that's distinctly not the case when we're working with textures. Texture coordinates add additional requirements into this algorithm. But fortunately, we can use exactly the same techniques we've been using to work out where we are in pixel space on the screen to work out where we are in texel space in the texture. And so, in addition to having dx and dy step sizes for pixels, we're going to have another set of du and dv sizes for texels, which means we can calculate the starting and ending points in texel space. But instead of filling in with a single colour, we need to now linearly interpolate along the scan line in texel space. So this means we need to count how many pixels there are in pixel space along this line, and therefore we can use the count of the pixels to give us our effective t value when we're interpolating to work out where we are along the line in texel space. So just to recap, when we're drawing a triangle and intend to texture it, we're going to send in some texture coordinates, u's and v values per vertex. And as we're creating the lines necessary to know where to start and stop drawing the horizontal scan lines across the textures, we're going to use exactly the same approach to give us a starting u and a starting v, and an ending u and an ending v, which will lie somewhere along the line between the two u and v coordinates represented by the vertices on that line. Once we have the start and end positions in texel space, we're going to linearly interpolate between them because our scan line is a horizontal linear line. And by counting the pixels as we're scanning, we can calculate a t value to give us a final u and v value, which is where we're going to sample the texture. I know some of you will be thinking ahead at this point and that this method isn't actually quite right. Don't worry, we'll get there. And so I'm going to add an additional function called textured triangle, which is going to take in x and y coordinate pairs, because we're in screen space, don't forget at this point, along with u and v coordinate pairs. Now I've not used the types because in keeping with the console game engine, you just pass in the values directly. The final argument is a pointer to an OLC sprite, which we're going to use to represent our texture. Thank you Visual Studio for making that look much better. Now that we're introducing a sprite into the mix, I'm going to store a pointer to a sprite in our main class called SpriteTexture1. And I'll simply preload our sprite in onUserCreate. I'm going to load the Jario sprite from the platformer game. The input to our function gives us 3 arbitrary x-y coordinates. I need to sort them in order of low y to high y. I'm just going to do this manually. But I'm going to make use of the standard swap command to swap the variables around. Now don't forget, we have to keep our vertices together, so the texture coordinate information must also move with the vertex information. So it's important to also swap the u's and v's. And I can use some creative cut and pasting to handle the rest of the swapping. So this quick bit of code has now sorted all of my variables based on the Y position on the screen. I'm now going to calculate various gradient and utility information that I need to draw the triangles. So starting off with one of the lines, I need a dy and a dx value. But at the same time, I'll also create a du and a dv value. Don't forget that pixels are effectively an integer domain now. You can't move things half a pixel. But the texture coordinates always remain in the floating point domain. So I've got one line on my triangle which I'm saying is dy by dx 1, and I'll have the other line of my triangle which is dy by dx 2. And again, I'm going to keep everything together as groups. As I iterate down each line, I want to record a step value for how many pixels I should move in x. And as we saw in the slides, there are 2 lines, A and B. So one of the lines will be stepping down the screen towards the left, and one was stepping down the screen towards the right. There are starting and end points along the horizontal scan line. And I also said that we should do exactly the same thing for our u's and v's along those lines. If the line between the 2 points on the triangle is horizontal, there is no dx, it's infinity. So we want to test for that before calculating the steps along the lines. And everything we do for one side we do for the other. So we've got our U1 and V1 step here is calculated exactly the same way. But you'll notice that I'm using the number of rows of scan lines in our triangle to work out how much change there is in texel space. And because we're working with a starting and an end, I do exactly the same for the other side. So now I've got all of these convenient gradient values, I can start to scanline fill our triangles. So as long as the line that we're looking at exists, i.e. it's not flat, we can assume we're drawing the top half of the triangle, i.e. from a singular vertex we're drawing out towards 2 vertices. And we know that we can safely do this until we hit our y2 coordinate. So we will draw from y1 to y2, because this is implied that y2 is either the flat bottom of a triangle or it's the middle of our entire triangle. The first thing to do is work out our vertex position along the edge. And so this is simply ax becomes our original starting vertex plus a count of how many x steps we should have moved based on how many rows we've moved down the triangle. And whatever we've been calculating in the vertex space, we're also going to do something analogous in the texture space. So I'm creating a starting u and v value in exactly the same way. So following one line we get a starting value, and following another line we get an ending value, which I've designated as su and eu. But there's a catch. Even though I know my y direction is going down, I've no idea really is one of these my starting and ending points. I just know that they are 2 points. So I need to now sort along the x-axis to ensure that I'm always drawing from start to end, i.e. I'm always drawing from an x value that is smaller before I move to an x value that is larger. This is reasonably trivial, because we can just look at our ax and bx, and if bx is smaller than ax, we swap them around. But don't forget to also swap our texture starting and ending points. At this point I'm going to add in 2 more variables, texu and texv, which are fundamentally the final point of the texture of which we're going to sample. And I can set these to be our starting location that we've just calculated. I know that I'm going to need to adjust these values as I scroll across the scan line, but the amount that I need to adjust them by changes because the starting and end point also changes. So I'll calculate a value called t-step, which is 1 divided by the number of pixels that makes up the scan line for that particular line on the triangle. And I will also bring in our old favourite t to represent where we're up to in our linear interpolation across the scan line. We're now up to the easy bit. We're going to draw the triangle. We just simply need to iterate from AX to BX, as each one of these locations represents a pixel on the screen. We can calculate text U and text V by linear interpolating between the starting point and the ending point of the scanline by our value t, but each time we get to a new pixel, we must increase t by t step. And finally, knowing that we're scrolling down the y-axis using I and across the x-axis using J, we can use the simple draw command which draws a single pixel. We don't use it that often in the console game engine, but it plots a single pixel at a particular location. And we'll specify what the pixel looks like by using the sample glyph function of the OLC sprite and the sample color. And we'll just feed those directly our U and V coordinate. And you would think after all of this that we might be done, but in fact we're not. We're only halfway there, but the second half is almost identical. And it's simply the case that this is assumed that the top half of the triangle wasn't flat. Now we've reached the midpoint of the triangle, so we need to change some of the parameters of our lines. We've now reached this location. So we've drawn the top triangle, we're now drawing the bottom triangle. None of our B-line coordinates have changed, but our A ones do, so we need to update them. And then just carry on exactly as we did before. So I can update all of our gradients just by taking into account the new point. Point 3 in this case, in our sorted set of points. And again, I'll calculate how much we're going to step change along the x-axis for these variables. And the nice part here is it's almost an identical loop to what we just had. So I'll start just by taking the whole loop and pasting it in. But we do need to make a couple of changes. Firstly, our loop is no longer going from y1 to y2, it's going from y2 to y3. One of our lines now starts at a different x coordinate and a different y coordinate. The other line, our B line, we can just carry on using the information we were using before. We've not lost anything. And again, with our starting point, we're now using new UV coordinates. And so it's just about keeping things consistently together. Everything else can stay exactly the same. It's now time to call our textured triangle function. And we'll have to pass in all of the points independently. So for our triangle, we've got the x and y coordinates of the vertices. But we've also got the additional u and v coordinates of the textures related to those vertices. So that's our first point, second point, and third point. The last argument to pass in was the texture itself. Well, I admit all of that seems actually quite complicated, but if you do look at the source code, you'll see it's actually quite a simple thing. We're just making some lines and slowly moving along them. But anyway, let's take a look and see how well it works. Well, nicely we can see Jario. Welcome back, Jario. Nice to see you again. And we can move Jario around, and it looks as if Jario is being successfully clipped and manipulated. Let's zoom in a little bit on Jario. Looks very nice. Oh, well, there does seem to be some distortion going on, although the clipping algorithm is working nicely. And it certainly looks like Jario is textured on all sides of the cube, even the tops and bottoms. But when the surface of the cube is near to the camera, we can see some sort of awkward distortion taking place. And if I try and find an extreme example like this, we can see that for one of the triangles, all of the pixels remain parallel to one of the edges. And for the other triangle, they remain parallel to the other edge. And they don't meet up in the middle. And this is fundamentally a problem. We haven't taken perspective into account in our texturing. Everything we've done has been linear interpolation, which means we're trying to attribute the same amount of information per pixel regardless of how close or far it is away from the camera. And so we must do something about this. If you follow any other texturing tutorials, they'll tell you this is because we've effectively created an affine map between the texture and the surface. And they'll go on to say other boring things such as, like, in the first PlayStation 1 games, this is exactly how texturing was done, and when the camera was near the edges of the walls, you saw this sort of distortion. I feel it's obligatory that I say exactly the same thing, because in other texturing tutorials that I've seen, everybody says the same thing. They then usually go on to say that perspective correction is a really difficult thing to do in software, and only hardware is capable of giving you real-time results that are worthwhile, and that's just not true. Perspective correction is actually quite a simple thing to implement, and perhaps for inspiration we should look at where we do the projection for our vertices. We took each of the points x, y and z and divided them by the omega values, the w value, and this had the effect of implementing perspective. Envisage a scenario where we have a unit quad laid down in front of us like this. So the distance from those two vertices is 1 and the distance from these two vertices is 1, but because of perspective we say that one edge is shorter than the other. As things get further away we know that visually they get smaller, and so when we're close to the camera our pixels are quite large. But as we get further away our pixels get smaller and smaller and smaller. And this gives the illusion of perspective. In fact, we exploited this for the Retro Racing arcade game. So as we're interpolating along the edge of our triangle, we need to take into account where the vertex is in Z space to give us a step change value which is different to take into account of the perspective. This means, along with our vertex coordinates where we divided by W in order to project them, we're also going to need a W and some division to effectively project our texture coordinates too. So starting with our vector 2D structure, I'm rather oddly now going to change this into a 3D structure by adding a W parameter. This makes it in many ways similar to the vector 3D structure, which is in fact a 4D structure because it has a W which we're using for normalization. We don't need to change any code now until we get to the projection part of the program. By passing our vertices through the projection matrix, we generated the W component to our vertex vector. And we're going to use the same W component to transform our texture coordinates too, because effectively the W component is in some way a function of depth. Before we destroy this W value through the division, because don't forget this divide will effectively divide W by W, so it'll become a 1, we're going to use that W to modify our texture coordinates. So let's do this for each point of our triangle. For each texture coordinate in the U-axis, I'm going to divide by the W component of our projected equivalent point. And naturally, what I do for U, I'm going to do for V. And this is where the relationship becomes important, because I'm going to do something a little cryptic here. I'm going to update the W component of the texture coordinate too, by dividing it just as I have done with the U and V. Now the W component was defaulted to 1. So we've now got a mapping from view space to projection space with perspective in the vertex domain, and we've got a relationship between that mapping in the vertex domain and the mapping we have in the texture domain. The relationship is 1 over the W used in the position perspective projection on the screen. We've added additional information now to our triangle. So I'm going to have to pass that information into our textured triangle function. So along with our U and V, I'm also going to add a W. 1, 2 and 3. And some commas for good luck. And that means we also need to pass in the W values, or 1 over W values, when we call the function. But what do we do with these values now that we've got them? Well, we have to maintain them along with all of the others. And we're also going to be interpolating these values with the others too. And you'll see that we'll interpolate this value no differently to how we've interpolated the position and how we've interpolated the texture coordinates. But this W value fundamentally has to play a role in the perspective correction of our texture sampling coordinates U and V. So I'm also going to include a text W value, which we'll use in our sampling calculations. We'll need steps as well. And so this really is a case now of updating every instance where we had U and V with a corresponding W component too. When we create our start U and V, we'll also need to create a start W. And therefore we'll also need to create an end W too. So I've gone and implemented interpolation for the W component now throughout the whole drawing routine. But where do we do the magic perspective correction? Well, there's only one place we can do it, and that's when we're sampling the texture. We will interpolate our W value, And I love how these things always come together, because when we've always talked about perspective, no matter what video I've done, it's always been x divided by z and y divided by z fundamentally gives you perspective. And that is no difference in this case. We just change our text u and text v coordinates by dividing them by our text w. Before we can successfully run this, we've got one more thing to change. We've added another component to our texture coordinate. We'll need to add this to the initializer lists. So let's take a look. Well, again, we can see Jaryo on a cube. This is good. And it doesn't seem to be flickering, nothing's wrong with it. And as we bring the camera towards Jaryo, we can see that the texels, they get smaller as they go into the distance. We've corrected for perspective during our texturing process, and we can see this on the top of the triangle too. It's nice to see all of the clipping coming in together. So there we have a really nice textured triangle. The first person camera is just proving a little tricky to see what's going on. So I'm going to bring back in our rotational theta just to make the cube rotate. And so there we have the soon-to-be world-famous spinning perspective-corrected textured Jaryo cube. Proving that you can do simple texturing in the command prompt. Now that we have a robust method for texturing our triangles, we may as well also load some texture information from the object files too, and have some fun with that. It doesn't take much to modify our load from object file function. In addition to the lines we're already sensitive to, we need to be sensitive to a line that begins with VT, vertex texture. And so if the line begins with a V, it's either a vertex or a texture coordinate, based on the next letter. Reading the face information is a little bit more tricky, so I'm going to add to our load from object file a Boolean variable that says, does this model have a texture? I'll default it to false, so most models won't. So if it doesn't have a texture, I want to do exactly what I was doing before. But if it does have a texture, I need to look at it a little differently. In this object file, we can see the lines that contain texture coordinate information. It's just a 2D pair, VT. But we see that the faces are now defined a bit differently. They're no longer just three numbers. It is a combination of the vertex, highlighted, and the texture coordinate, separated by a slash. So we need to parse the whole line slightly differently. How we do that exactly, I'm going to say is beyond the scope of this video, but basically we count through the characters and see what we need. Let's keep this one about graphics. Since we're no longer interested in the cube, I'm just going to comment it out. And instead, I'm going to load a mesh using the function we've just modified from an object file that I found on the internet. I'm also going to make sure that I load the texture that corresponds to that mesh. And the last thing I want to remember to do is remove the theta value, so we're not rotating the world around. I've made a couple of other little cosmetic changes, but let's take a look. And what we have here is undeniably, although a few glitches here and there, the first level of the Spyro the Dragon game for PlayStation 1. The game itself is just a single OBJ file, and it comes with a texture. Now you'll see there's a few little artifacts in the texture. We'll talk about that in a minute. But it's fully rendering quite nicely, so this is rendering at about 8 frames per second in the console. So I'm just going through this corridor here. And there's the little castle. Now if you remember, this castle I think used to have a whirlwind in it. So you'd go in through the door, inside, and get shot up to the top. There we go. And so this is accumulation of texturing with perspective correction, clipping of the triangles and sorting of the triangles to make them work. But there's a few things that aren't quite finished. One of the things to note is that occasionally you'll see polygons disappearing, and that's because we're sorting triangles. So you look at the edge of this pier, we're sorting triangles based on their distance from the camera. Also, the performance is a bit sucky. I mean, I know we're doing it in the console, but it's still quite slow. And this is because the model contains many thousands of triangles, and we're sorting by triangles. So it's now time to add a depth buffer, because sorting by triangles isn't very efficient. And as you can see, when the triangle itself, the whole triangle, is behind another one, then large chunks of the scene can disappear. This isn't ideal. So let's look at adding a depth buffer to the scene, and I've left this till last because it's really quite trivial. To the main class, I'm going to add a variable called pDepthBuffer, which is a pointer to an array that I'm going to create. And I'm going to create that array in onUserCreate to be exactly the same dimensions as the screen. So every pixel on the screen is going to have a floating point depth value associated with it. When I draw into the scene, I'm specifying an x and y coordinate in screen space. I'm also going to draw into my depth buffer the w value. But I'm only going to allow that at all if the w value is greater than what is already in the depth buffer at that point. So before we draw any pixels, we check to see, are there any pixels that are in front of it? Because if there are, we don't want to draw this one on top of it. So now when we clear the screen, we don't just want to reset all of the screen pixels to a certain colour, we also want to clear our depth buffer. We set all of the depth values to 0. And it's by no coincidence that at this point was where we were also sorting the triangles. I'm going to choose not to do that at all anymore. I don't need to. But I'm going to retain the ability to sort the triangles because there are things that do. If you have, for example, windows that have transparent or translucent effects, then they still need to be rendered in a back to front order. But for now, I'm just going to throw all of my triangles at the screen and let the depth buffer sort them out. No complicated sorting routine anymore. So let's take a look. Well, firstly, the performance is shot up by a few frames per second, so that's a good thing. And I don't see any large triangles popping out of the walls and scenery as things are getting sorted, so I believe that the depth buffer is working fine. I'm a little concerned, though, about these lines that I'm seeing everywhere. And this drove me nuts. And I was completely convinced that I just don't know what I'm doing and that I've got some horrible rounding errors somewhere in my texture, until I loaded up the model that I downloaded from the internet. Here I've loaded up the OBJ file and its texture in Blender. We can see it looks very nice, smooth. You don't see sort of glitches and artifacts everywhere. At least I didn't think there were any until I disabled the wireframe view mode and looked at it. The texture itself even Blender can't handle. It is the model and the texture configuration which is causing the problem. This has convinced me enough to believe that the way I'm texturing the triangles is actually quite accurate. I thought it might be useful to try and think about, are we hitting the limitations of the console now? For example, I don't really believe that the geometry handling code, i.e. the software rasterizing code, is very slow. How much effect is the Windows rendering process of the command prompt having on the performance of the algorithm? Well, there's one way to find out, and that is that we run everything, but we just hard code out of the console game engine the update to the screen. So all of the calculations and everything takes place, we just choose not to display it. And let's see what the frame rate is like then. So in the console game engine, this is the line responsible for updating the screen. I'm just going to take that out temporarily. And so I'll run it, and we can see straight away actually the frame rate of the game itself is about 210 frames per second, at least flickering by on my screen. And don't forget, I'm also recording this as well. So that's suggesting that actually the rendering algorithm that Windows uses to display the console is very slow. We can analyse this further by looking at the GL version of the console game engine too, because this doesn't use the console as part of its output. So here the frame rate is about 140 frames per second, and it's indeed much smoother. So this, I feel, starts to beg the question, are we beginning to reach the limitations of the console? I still like it, I think it's a lot of fun, and I think we're doing deliberately silly things with it right now. But nonetheless, if we wanted to pursue graphics in any serious way, I think we need to start thinking about something else. And so there you have it. A bit of a rush, but texturing in the command prompt as part of our 3D Game Engine series. Anyway, if you've enjoyed this video, please give me a big thumbs up, have a think about subscribing, and I'll see you next time. Take care.